Alright, in this video I'm going to be going over the photoelectric effect question from the 2007 NZQA paper. So in this question we are given some data, and then we're told historically photographers have used light meters containing photocells that are modeled on the photoelectric effect. A photocell consists of a vacuum tube containing a curved sheet of zinc metal as the cathode and a metal pin as the anode, as shown in the diagram below. When light shines on the photocell, there is a current in the circuit. A very sensitive meter measures this current. Alright, and there we have the diagram. Describe what causes a current in the circuit. We can say when light falls on the cathode, electrons are ejected. They travel, let's just do a full stop there and write properly. They travel to the anode and complete the circuit. Causing a current. We should probably mention that this is due to the photoelectric effect. Electrons are ejected, we can say here, by the photoelectric effect. Okay. Explain how changing the brightness of the light affects the size of the current in the circuit. Brighter light contains, well, let's just say it a little bit more effectively here. So if light is brighter, more photons will hit the cathode per second, transferring their energy to electrons. Thus, more electrons will be ejected per second. More charge will flow across the gap, causing a larger current. Note that we're assuming the light has high enough frequency to overcome, well, for photons to overcome the work function of the zinc cathode. Okay, so have we done that now? Explained how changing the brightness of the light affects the size of the current. We've explained that brighter light causes more photons to hit the cathode, and therefore more electrons will be ejected, therefore a bigger current if the photons have high enough frequency. Okay, cool. So to investigate the properties of the photocell, a variable voltage supply is connected to it, as shown in the circuit diagram. Using a color filter makes the light hitting the zinc cathode monochromatic, so in other words have only one frequency. The voltage is changed until there is no current in the circuit. This voltage is a measure of the maximum kinetic energy of the released electrons in electron volts. By using different color filters to change the frequency of light hitting the zinc cathode, a graph of maximum electron kinetic energy in electron volts against frequency is drawn, and here's that graph. Okay. From the graph, determine the threshold frequency of zinc. Now the threshold frequency is the minimum frequency at which electrons are ejected, and that is, in other words, where they emerge with zero kinetic energy. So that will be the x-intercept, and that will be here. Each of these little units here is 0.1, and it's exactly halfway in between, so it's 1.05. So we can say 1.05 times 10 to the 15 hertz, and we might just mention that that's the x-intercept to show how we got it from the graph. The equation for the maximum kinetic energy of the released electrons in joules is Ek equals hf minus phi. Using information from the graph, calculate a value of Planck's constant and show your working. Okay, so it's typically the gradient, except here we're given the units for the y-axis are in electron volts. So we can say that Planck's constant is given by Ek minus phi over h. Right, that's just rearranging this equation. And then we can just determine what Ek and phi are in electron volts and convert those to joules and then divide by h. Sorry, not h. By F. Right, that should be equal to H. So let's check out what those are. So we can choose any point on this graph, can we? Ek here, and phi is this. So if we choose this one, Ek equals 8. So let's do that. So it's 8 minus negative 4 electron volts divided by, and the change in frequency here is 3 times 10 to the 15. So what we really are doing is working out the gradient here, because we're really taking that rise and we're dividing it. It's not negative 4, it's negative 4.1. No, it's not. This is 4 to 6. So each of these units is actually 0.4. So that's 4, 8, 12, 18, 16, 2. Yeah, okay, so that's negative 4.4. And this is positive 8. So this difference here, that's Ek minus phi, which is plus 8 minus negative 4.4, which is 12.4 electron volts. So we can say that here, Ek minus phi is equal to 8 minus negative 4.4, which is equal to 12.4 electron volts, which is equal to how many joules? 12.4 times 1.6 times 10 to the negative 19, which gives us this value, 1.984 times 10 to the negative 18. Joules. And the frequency of that 8 one, whoops, if we just go back up here, that was 3. So this run here, whoops, this run here is 3 times 10 to the 15. F equals 3 times 10 to the 15. And so we get our final value for H. H is equal to 1.984 times 10 to the negative 18 divided by 3 times 10 to the 15. Which is 6.613 times 10 to the negative 34. 6.613. That's in joule seconds. Note that this isn't exactly like the textbook value. Question E asks us to determine the threshold frequency for a metal that releases an electron with maximum kinetic energy of 3.94 times 10 to the negative 20 when light of wavelength 4.01 times 10 to the negative 7 shines on it. So this is EK, and we have this number here, which is lambda, and we know that EK is equal to HF minus phi. We're asked to find the threshold frequency, which is not already in here. But we know that the threshold frequency relates to phi. Oops. Phi is going to be equal to H times the threshold frequency. Because when the photons have exactly the threshold frequency, then their energy is exactly equal to the minimum energy required to release an electron, which is phi. And we also know that F is equal to c over lambda, because the photons travel at the speed of light. So the wave equations F equals v over lambda becomes c over lambda. And what we'll do then is just substitute these two equations into this first one. So 1, 2, 3. So we go 3 and 2 into 1. And we get EK is equal to hc over lambda minus hft. So what we'll want to do then is rearrange this for ft. So we can see that hft is equal to hc over lambda minus ek. So then we'll cancel that h, and divide here by h. So we see that the threshold frequency is c over lambda minus ek over h, which is 3 times 10 to the 8 over 4.01 times 10 to the minus 7 minus 3.94 times 10 to the minus 20 over h, which is 6.63 times 10 to the negative 34. Alright, so let's solve that. So 3 times 10 to the 8 divided by 4.01, was it times 10 to the negative 7? Yes. Times 10 to the negative 7. Hold on, let me just make sure that I've got a clean. So let's try that again. 3 times 10 to the 8 divided by 4.01 times 10 to the negative 7. And then we wanted to subtract from that 3.94 times 10 to the negative 20 minus 3.94 times 10 to the negative 20 divided by h, which is 6.63 times 10 to the negative 34. And that gives us this enormous number. Let's just change that to standard form. So 6.89 times 10 to the 14. Hertz. Okay, so that's the threshold frequency. Alright, so that's a sample question on the photoelectric effect with a couple of nice tricky questions in it. I do recommend that you work through a couple more practice questions.